we're going to quickly go over what we did in the last few minutes of the last class. You've of course been questioned about it in the quiz, but we'll go over it again anyhow, right? So everybody remember this equation, where it came from. Does everyone remember this? Raise your hands if this made sense, right? So it's simple. The simple idea was that if I have a previous layer, yk minus 1, and I have the affine values of the current layer, then if I can put all of my z values in a single vector, all my y values in a single vector, yk minus 1, and the connecting weights in a matrix and the connecting bias in a vector. Now, if this layer is size n and if this layer is size m, then what is the size of the weights matrix, Pechi? You. So if I have the kth layer be size n and the k minus 1th layer be size m, what is the size of the weights matrix that connects the k minus 1th layer to the kth layer?
3m by n.
Pardon me?
3m by n.
M by n or 3n by m? What did you say? What is it going to be, guys? N by m. Why is it n by m? One row per output, right? And every row corresponds to all the weights going into one new neuron. What is the size of the bias vector? N. It's going to be n cross 1 if you're using column vectors. And so that gives us zk equals wk times yk minus 1 plus bk. Right? Everybody clear with this? And of course, the output of that layer is simply the activation function applied to the affine values. And this gives us our forward pass. We can just set all of the inputs, the 0th layer to the input. And subsequently, as you go through the network at each layer, first you compute the affine value by applying an affine transform to the output of the previous layer. And then you compute the output of the layer itself by applying the activation to it. And the output of the final layer is the output of the network, correct?
I'm so sorry.
Yeah.
It's a dumb question.
Yes.
What is Z?
Which z?
Like ZK?
Okay, can somebody answer her? What is zk, Jesse? So, okay, what are the two stages in a neuron? When you compute an active neuron, what are the two steps of the of computation? Jaya, can you tell her?
One is like affine computation of all
And please speak up. The one is the first is the affine computation, and then?
of all inputs, and then you apply the activation.
Then you apply the activation. So to answer your question, Abhi, there is when at every neuron, remember what we did. Within a neuron, first you computed an affine value, then you applied an activation, right? Okay, everybody get that? Does anybody else have this question? It's not a stupid question. It keeps coming up because we fly through symbols. Okay? If anyone else has this question. All right. Now, okay, here is some more questions. I have a scalar function. This is a scalar. The scalar is 1 cross 1, right? And it is a function of some vector n, which is n plus n cross 1. What will the derivative of this guy with respect to x be? What is the size of this one? Anyone? What is the size of this one? 1 cross n, right? So if the input is a column vector, the derivative is going to be a row vector. That's the only way it works, okay? Extending this, if this was a function of a matrix, which is n cross m, what is the size of the derivative of the loss with respect to, of the scalar with respect to w? Can I hear that aloud, please? Thank you. It's going to be the transpose, right? M cross n. So these are things that you will always use to verify the sizes of your computation. If you're not getting these sizes, then something is off, right? Now, And so when we have a derivative of a vector when the function itself computes a vector and is also the function of a vector, then we saw that we can think of the entire thing as a stacking of scalar functions. The vector y is just a vector stacking, vertical stacking of several scalar functions, one for each y. And therefore, when I think of the derivative of this function with respect to z, it's simply going to be the stacking of the derivatives themselves, right? And so the ith row in this derivative is going to be the derivative of the ith y term with respect to the input. And this matrix is what we called a Jacobian. Everybody remember? All right. Raise your hands if you did. I'm going to keep making you do this because this is the only way I keep you awake, all right? So bear with me. Now here is the chain rule. I said let's say some what did I call this? What am I calling the variables? Some y equals y of z of x, right? If I have this, then I can always write, if I in terms of derivatives, if I want to express delta y in terms of z, then what is this term over here? Jishwan. What would that be? Yes. You know the answer. Somebody else? Okay, I'll help you with this one. This is simply going to be the derivative of y with respect to z, correct? Okay. Everyone clear about this, right? What is if I write the same thing for delta z in terms of delta x, what is this going to be? Same thing, right? The derivative of z with respect to x. So now if I combine these two, I can replace this term here by this term here, which will give me delta y equals the derivative of y with respect to z times the derivative of z with respect to x delta x, right? So what is this guy here? This term? Okay. Pardon me? Bill? What would that term be?
It's the gradient of x to y.
Is it the gradient?
The derivative.
It is the derivative, right? Now something else. Can I change the order of those two the derivative terms over here? Can I write this instead as delta zx delta, nabla zx, nabla y, z. Can I write this instead of this one? Why not? They are vectors or matrices, the sizes will not match up, right? Things have to match in size. And so observe what's going in. The first term is the derivative for the outermost term. The second term is the derivative of the inner term. If I have a chain of equations, let me ask you this one question. Suppose I have some L equals, yes.
If you put up the whiteboard, people in the back can see that more clearly. Like the one behind you. Wait, like the one that you finished writing on, if you
It doesn't go up, that's attached.
Oh, really?
Yes, that's the bottom one, right? They're very nice to me. They put all the boards that I don't want up there where I can't reach them, right? So suppose I have something of this kind, D of A of B of C of X. Okay. Then if I want to write the derivative of L with respect to X, can somebody give me the chain rule? Someone at the back. You in the middle with the name tag, with the black, or is it black? Yes. This one here. Is it starting from the middle? Which order? So how would I write this? Is this going to be derivative of c with respect to x, derivative of a with respect to b, derivative of d with respect to a? Is this correct? What's wrong with it? The order is wrong. You have to go outwards in, right? Otherwise the sizes will not match. So, okay, everybody clear. This is going to hold regardless of whether x, y, and z are scalars or vectors. It doesn't matter what the variables are, the sizes of the variables. If they're scalars or vectors, this relationship is going to hold. Okay? Which brings us to these two equations. Firstly, over here, in any layer, I have the affine value z to which I apply my activation function y, right? And now the output of the layer directly affects the output of the network itself, and therefore it affects the divergence, correct? And therefore, I can say the divergence is a function of y. And so if I want the derivative of the divergence with respect to z, that's going to be the derivative of the divergence with respect to y times the derivative of y with respect to z, because I'm going outwards in, right? That's why we have the backpropagation. And this, of course, is just the Jacobian. Everybody clear with this, right? And then secondly, this was the other one. If I have a layer and I have already obtained the derivative with respect to the z at the layer, now z is a function of y, right? What is the derivative of z with respect to y over here? That's just going to be, can I hear it aloud? W, thank you, right? That's just going to be w. So if I want the derivative of the divergence with respect to y, that's going to be the derivative of the divergence with respect to z times the derivative of y with respect z with respect to y, which is simply the derivative of the divergence with respect to z times w, right? So that is transferring it all the way back here. What about the derivative with respect to b? I can use the same chain rule, and the derivative of the divergence with respect to b is going to be the derivative of the divergence with respect to z times the derivative of z with respect to b. And that's an identity matrix because z equals b plus something else. So that's just going to give you this term. Yes?
So I have a question for the derivative of d with respect to w. Do we need to take the transpose of y? Because y is currently a column vector. I believe it should be a row vector.
Which one? The derivative?
Of d with respect to w.
Okay, let's work this out, right? I have the derivative of the divergence with respect to z. This is fine, okay? And now let's just take the sizes. Let's say yk minus 1 is size n and zk is size m. What is the size of the weights matrix? What would it be? N cross m, correct? N cross m, okay. What is the derivative of the divergence with respect to z?
M by n.
Z with z. The size of yk is n, the size of zk is m. What's it going to be? 1 cross with respect to z, right? That's going to be 1 cross m, 1 times m, right? So this is going to be 1 times m. What must I multiply this? What will the derivative with respect to y be? The size? 1 cross n, right? There's going to be 1 cross n. So what must I multiply this guy by to get the right size? That's going to be m cross n. What is the shape of that? What is the shape of w? Am I losing you guys here? What is m? What is the size of w? W is going to be m by n. What is this one here? Okay, so where's the transpose?
The transpose of that is n by m with which we are multiplying.
This is w. Where is the transpose? Right? This one? This guy, the output is m. Okay, correct. M cross, yeah, you're right. You're right, okay. So, but you see everything fits, right? All the sizes fit. The one crazy thing over there is, so again, the point is you have to verify the sizes. You can't just trust me. I can make mistakes, but you have to verify the sizes. And the fact that the derivative of z with respect to y is w is obvious. Delta z is going to be w times delta y, right? Now this last bit is crazy. Because if I continue to use the chain rule, you should have said the derivative of d with respect to w should be the derivative of d with respect to z times the derivative of z with respect to w, right? That's not what it looks like. But here's why this equation works out. Z is a vector, right? W is a matrix. What would the size of z, or the derivative of z with respect to w be? Anyone? Every element of z is a function of w, right? So what is the derivative of each element of z with respect to w? The transpose of w. I'm stacking those, one for every z. So the derivative of z with respect to w is going to be a cube. It's a tensor, correct? Everybody see where that comes from? But then if I just sort of work through the arithmetic, it just works out that in the end you get this equation. So this is not a straightforward application of the chain rule. When you simplify it, you get this equation, and once again you will find that the size is right. Why is the size right? Okay. So if I have y is size, say, n cross 1, yk minus 1, zk is, say, size m cross 1, right? Then w is going to be n cross m, correct? And the derivative of the divergence with w is going to be m cross n. This we agree, correct? The derivative of the divergence with respect to z, what is it going to be? It's 1 cross m, right? So when I multiply y by the derivative of the divergence with respect to z, that's going to be n cross. Am I getting my sizes mixed up? But you get the idea, right? I will get my sizes mixed up. But the sizes will work out, even if they didn't when I tried to write them. Okay. Yeah.
Yes, I have a quick question, especially when you're doing the backpropagation, right? Is there at any point where we have to do like element-wise multiplication, and if there is like
no, the whole thing just works through this. It's very rare that you will end up in a situation where you have to do
element-wise.
Yeah, you'll get element-wise multiplication of matrices sometime later, and something we'll see a few lectures from now. Okay.
And then there's a separate notation for that.
That's a sure multiplication, yes. Okay. Anyway, and so this gave us our backpropagation rule. The first thing, it compute the derivative with respect to the output of the net, move a step back by multiplying that derivative by the Jacobian of the output activation, move a step back by multiplying that by the weights matrix to get the derivative here, but then also use the other two formulae to get the derivatives with respect to the parameters. And then you can keep moving back to compute the derivatives everywhere. So the entire backpropagation had this kind of pseudocode. You'd go through all of the data. For each of the data instances, you'd compute the output, and then you would compute the divergence. So the overall loss is the average of all of the divergences, right? And then you can work your way backwards from there and just compute the derivatives for each training instance, average the derivatives across all of the training instances, and plug that into your gradient descent rule. And this should work out. Yes, Neil?
So this is regarding the part where you discussed the cube. So if you're doing gradient descent, what part of the cube would be used to update those weights?
The whole thing sort of simplifies to this equation. So there is no cube once you're done with it. It simplifies this to this equation. That's all, right? So there is no cube once you're done with it. Anyway, there's a poll. That was supposed to take 10 minutes. It took 20. The poll number is 485. So ignore this, please. 485 for the first one. 485 again, guys. Done? All right, thanks guys. Okay, let's move on, right? Story so far, neural networks, we saw universal approximators, but we must train them to approximate any function, and they are trained to minimize the total loss in a training set. And we do this, we use variance of gradient descent to minimize this total loss, right? Let's move on. Now, does backpropagation always give you the correct answer? Now, we're going to look at that, and we're also going to look at things like convergence, rates, restrictions, and so on. And I might not actually finish today's lectures because I'm running over time, but then we'll catch up or do an extra half hour at some point. Okay. Now here's the first question for today. Assume that you perform backpropagation, gradient descent basically, and then you actually find the minimum of the divergence function that you're trying to minimize. Will this give you the answer that you want? Always, right? So now to give you ask this question, let's go back over here. Remember that you want to train your function, your network, to minimize classification error. That is really the objective, right? So when we had this, we wanted to, the way we saw when we were using threshold functions, we saw that changing the threshold didn't affect the output. It didn't affect the error count. And so which is why we chose not to use threshold functions, right? Instead, we said, let's use a smoother version of it. And now instead of just counting the errors, we can actually find the total distance between the actual output and our function output. And we can use this as a proxy for the error count and try to minimize this instead. Will minimizing this always minimize this guy? Anyone, what do you think? Yes or no? You all think yes? How many of you think yes? Raise your hands. How many think no? Raise your hands. And the rest of you have no opinions? So okay, let's try this again. How many think yes? And how many say no? Many of you still don't have an opinion. So we're going to try this a third time, right? How many think yes? Raise your hands. And how many think no? Some of you are very stubborn. I'm giving up on you, right? All right. So let's try this question. Consider this training set, right? I have a bunch of blues and a bunch of reds. Are the blues and reds linearly separable over here? Yeah. Right, okay. Now, so if I were to use the perceptron rule, would it find this boundary? Yes. Because it always does, right? What about backprop or gradient descent? That would also, with the smoothed curve, it should find the right boundary, right? Now let's try this guy instead. I now add one training instance, extra training instance right there. Are the classes linearly separable? Yeah. Will the perceptron rule find the classifier separation? Right? What about backprop? Why not? Okay. Can anybody tell me why not? Yeah.
You'll reach like a local minimum stop.
So here's what happens, right? I can have an infinity of these guys. And I can have one tiny little instance. So how much will that one instance contribute to the overall loss? When you're averaging things out, it's really not going to make a tremendous difference, right? Unless you allow your weights to go to infinity to account for this, which you usually won't. For any finite set of weights, what backprop is going to give you is this guy, right? It will be the minimum of your function. Now suppose I flip that guy around and move it here. Once again, the classes are linearly separable. The perceptron rule will catch it. Backprop is just going to change the answer a little bit, right? I can put it somewhere else. And now again, the perceptron rule will catch it. Backprop is going to give you a little wiggle, right? Now if I go through these slides, look at the boundaries that the perceptron rule gives you in each case, and the boundaries that backprop gives you in each case. When you use the perceptron rule, that one instance can make your answer swing wildly, right? backprop is going to be sort of kind of wiggle your answer. Which of these two behaviors do you think is more reasonable? Because you don't want one instance to make your thing swing around like a madman, right? And so in technical terms, we will say that the perceptron may change greatly upon adding just a single instance. It fits the training data well. So it makes no errors. It has low bias, right? On the other hand, it has tremendous variance. Just one instance can make the thing swing around. Backprop has a bias. It is biased towards the majority. If you have one thing swinging around, that's not going to make a big difference to your training instance, to the solution. But it doesn't have variance. And that's, in our books, that's a good thing. Yes, Jeffrey?
A question. So regarding the statement at the start of this discussion, do you mean the divergence function as in the idealistic function, or do you mean the approximation of the risk?
So when we're speaking of the divergence function, we're always speaking of this guy, right? You cannot use backprop with this one. So using the divergence function, which would be an L2 divergence or a Kullback-Leibler divergence.
So is it an average, or are we just assuming the distribution and taking the distance?
What do you mean?
Because a few lectures back you mentioned that the true divergence is never found. We always approximate it using.
So this is where we're speaking of the loss over here. The loss is the average divergence over the training set, right? So, okay, everybody comfortable with this? So this is not restricted to just single perceptrons. I can have a complicated neural network, and an MLP is going to learn maybe a complicated decision boundary of this kind. If I just add one noisy training instance over here, it's not going to go swinging around and go over there. It's probably going to stay mostly like what it was in the first place, because one instance is not going to make your loss function change so dramatically that the whole solution moves. And in our books, this is a good thing, right? Adding a few spoilers, these are, the original paper that cites this words gives you this explanation called some spoilers. Yes, Oren?
Will it always fail to separate, or are there cases where you initialize where it can separate all of them?
So again, I'm assuming that you're finding the minimum of the loss function, right? So that's independent of the initialization, right? Yes.
If we train the backdrop over and again on the same spoiler, basically increasing the.
I'm speaking of finding the global minimum, so it doesn't matter, right? There's a very nice paper by Brady and Sloaney way back when, which explains this in great detail. It's on the slides. Take a look. Now, if you let the weights go to infinity, this logic doesn't hold. Because, what is a sigmoid with infinite weights? It's a threshold, correct? But in reality, you never will. Now, so backpropagation will often not find a separating solution, even though the solution is within the class of functions learnable by the network. And that is because the separating solution is not a feasible optimum for the loss function. So this is independent of your initialization, right? One resulting benefit is that backprop trained neural networks have lower variance than the optimal classifier for the training data. The optimal classifier will separate the data, but then that may not be what you want, right? So going back to our example with these dots, if I had something of this kind, what is the optimal, actually not something, so but let me try something of this kind. So suppose I have these and I have these. What would the optimal classifier over here be? The optimal classifier over here is going to be something of this kind, right? Do we want that? No. And so backprop won't usually find that. But if you had something that actually found your optimal classifier, you're going to get this garbage. Okay? So meaning getting a zero training error can be a bad thing if it means that you're getting this. But then you shouldn't if your network is properly configured and you have the right restrictions on it. Anyway, this is actually 468. Something wrong with the poll? There's no 468. What is the number?
468.
There is no 4.
Is it not visible?
You got to make it visible, right? Is it visible?
Yeah, it is visible. This relevance changed.
नहीं आ रहा है.
Because they made the permission wrong or they edited.
Okay, let's move on, guys. There seems to be we are having canvas errors and Piazza errors. Yeah.
Can you not use both? Like, can we not use a combination of a perceptron and a backpropagation?
You can't differentiate the perceptron, so it's out of the question anyways, right? So, all right. So here is the question. Minimizing the differentiable loss function will also minimize classification error, true or false? The answer is false, right? Okay. So now we assumed that things are not going to work necessarily as you would want them to, even if you got to the actual minimum of the loss function. But then what does the loss function look like? A typical loss surface is going to be very ugly, right? And it's going to have lots of local minima. So how will your training actually behave? Now, I have a lot of text on the slide, but let's ignore the text on the slide. Let me give you a simple example, a simple explanation over here. So let's say your training network. So here's something. How many of you read the business about the Hessian in the class last time? Some of you must have got the Hessian question, right? What was the Hessian? Can anybody remind me? It is a matrix of the second derivatives. What exactly does the Hessian signify? So suppose I have a function of this kind, and let's say a function in 2 dimensions, right? And if the function is a bowl, then if I look at the bowl from the top, it's going to look something like that, right? And I can have a bowl that's kind of oriented with the axes, or I can have a bowl that's not oriented with the axes, right? If the bowl is oriented with the axes, these are the principal directions of the bowl. If the bowl is not oriented with the axes, these are going to be the principal directions of the bowl. It's not going to be the same as the axes. Regardless, if I have a quadratic function, for instance, right? If you look along the axis, the function is going to be a quadratic. Now, here is the thing, right? If the second derivative of the function, what is the second derivative of the function? It's the first constant in a quadratic, right? If the second derivative is positive, is this guy a minimum or a maximum along that direction? If it's a negative, it's a maximum. Now the second derivative along the principal coordinates of your function are the eigenvalues of your Hessian matrix. Okay, so when you compute a Hessian, for a function like this, the Hessian matrix is going to be diagonal. And the diagonal terms are going to be the coefficient of the second derivative, right? For a function like this, the Hessian is not going to be diagonal. But then if you looked at the eigenvalues of the Hessian, the eigenvalues are going to give you the second derivative along each of the orthogonal coordinates, right? Now suppose I have a 1 million cross 1 million matrix. So this means this is my Hessian. How many parameters would this function have? Pardon me? The parameter, the function, is going to be 1 million, right? Because you're speaking of the second derivative, 1 million cross 1 million. How many eigenvalues would it have? So this function is living in a 1 million dimensional space, right? How many eigenvalues would this Hessian matrix have? 1 million, right? If I were to flip a coin to decide the sign of, okay, the sign of the eigenvalues, what is the likelihood that all of the eigenvalues will be positive? That's really, really small, right? In general, what is going to happen is that your eigenvalues, some collection of them are definitely going to be negative. Some of them are going to be positive, right? If I'm looking for a minimum, I want them all to be positive. Now, what happens if I have a function where at some point the derivative is 0, some of the eigenvalues are positive and some of the eigenvalues are negative? If that happens, what it means is that if I have the x direction and the y direction and I'm plotting the function, it means that along the x direction the function looks like so. Along the y direction it looks like so, right? This looks like a saddle, right? And from purely statistical logic, it's clear that you're going to have many more saddle points than you're going to have real minimum. Is that making sense to you guys? Right? So typically, anytime you come to a derivative, the location where the derivative is 0 is going to look like this. It's not really a minimum. There's one direction in which it's a minimum. But in many other directions, it's going to be actually a local maximum, right? And so if you just use gradient descent and the thing sort of tapers off, with high likelihood you're stuck in one of these things, right? Maybe you want to perturb it and keep going on, right? Anyway, so for large networks, the loss function may have a large number of unpleasant saddle points or local minima, which backpropagation could find. If all you're using is the gradient as your criterion, we will see how we will be using something more than gradient later on, okay? Now, in the discussion, we've assumed that the training arrives at a local minimum, or at least at a local location where the derivative is 0, right? Which could be a minimum or even a saddle point. So where it arrives at is one question, but here's a different question. How soon does it arrive there? How fast does it get there? This business of how fast it gets there is the question of convergence, right? And it's very hard to analyze in MLP because it's a very complex loss function, but let's take a look at something that we can understand. We are going to keep falling back onto this so-called streetlight effect. You've all heard of this joke. Some guy loses his keys in a bar and then is found searching for them under a streetlight because that's the only place he can see. What's the point of searching where it's dark, right? So we're going to use this streetlight effect and use examples which we will understand. But then the first thing, some definitions, we're going to assume that the functions that we are using, our loss function is convex. When I say my loss function is convex, it means it looks like a bowl, right? So if I have a function, if I take any 2 points on the function, and if I draw a line across those 2 points, that line must either lie on the function or above it. If at any point the function actually, you have the line has the ability to go below the function, then the function is not convex, right? So these things are easier to analyze than this guy. Similarly, you can speak of convex sets. If I draw a line between any 2 points inside the set, every point on the line must remain within the set, otherwise the set is not convex. So these are convex sets, this is not, right? We're going to be assuming that everything is convex for now. Now, what do I mean by convergence? Remember, we are speaking of gradient descent. You're starting at some point, and you're taking small steps, one step at a time. And if you start off at some point and slowly arrive at the minimum, then you're converging to the solution. You're actually sort of arriving at the solution, right? You could also do this. You can get somewhere close to the minimum and keep bouncing around without actually getting to the minimum. This is jittering. This is not convergence. Or you can do this. Instead of arriving at the minimum, you can keep sort of diverge and go far away from it. And this would be divergence, right? And we're going to see what are the conditions under which these things happen. All right, Ron, what's the question? Sorry.
Do we consider convergence to be like within some epsilon? Because I imagine, like, if you look at it at fine enough scale, it would just jitter around.
Yes. No, it's always going to, it will prove When we speak of convergence, typically what this means in a mathematical sense is that if you wait long enough, it doesn't matter how small the ball is, you're going to end up inside it, right? But I won't get into the details of it. Okay. So now to explain convergence, I'm going to start off using this guy, and you guys are going to help me. Someone at the back again, because suppose I have a quadratic function, and I'm going to write quadratic functions in that manner: half of AW squared plus BW plus C. I like the half because when you take derivatives, the 2 goes away. That's how we define our losses, right? Now that loss function that quadratic function is going to be something like this, right? Can I solve for this, for the minimum? Okay, for this, is this function guaranteed to have a minimum? Regardless of A? What must the sign of A be for this to be a minimum? What will it be if A is negative? It's going to be a maximum, right? That is going to be the second derivative, number 1, right? Secondly, can I solve for this minimum in one step? Everybody give me a combined yes. Why? It's quadratic, right? Trivial. Okay. Now, if I want to use gradient descent, what will I do? I'm going to start at some point, and I'm going to just say, x is going to be x minus some eta times dy over dx. This is my gradient descent rule, correct? Now, suppose I start off at some point. What is the fastest way to get to the solution? Pardon me? So this is the rule I'm going to be using, right? What is the fastest way to get to the minimum? I can take a learning rate that just gets me to this point immediately. Can you pass the sheet out for the attendance? Pass it, okay, right? We're getting fewer and fewer people in class, so we'll have to begin putting the attendance up on the list. Right, yeah. There are 3 sheets going around. Please, guys, make sure to sign, right? Okay, so can anybody tell me what this learning rate is going to be that gets me here in one step? How would you do it? Pardon me? Can anyone tell me how I would get this? Yes? I can't hear you. Okay, so so how many of you have heard of Taylor series expansions? Raise your hand. Right? If you've heard of Taylor series expansions, and let's say I start off at some point x0, right? What is the Taylor series expansion around x0? One of you at the back, you there, can you tell me? Far corner, right there, the lady there. Yes, you, yeah. EG, I can't see EG, yes. So what is the Taylor series expansion around x0? Somebody else want to take a shot? Yes, Maxwell?
It's like x minus x0 over 0 factorial times f of x. And then like an f prime of x, and there's a 2 factorial. And there's like an f prime.
Okay, so he's getting there. He's guessing. He's mostly there, but he's guessing. Someone want to be something more? Give me something more concrete. One person. Yes, Oren.
If I remember right, it's the summation from I equals 1 or 0 to infinity of the ith derivative at 0 times x minus 0 to the ith power over I factorial.
X minus x0 to the ith power over I factorial, right? Okay, this is going to be, over here it's going to be f of x0 plus f prime of x0, x minus x0, plus f double prime of x0 times x minus x0 squared over 2, right? Do I need to add a third derivative over here? Why not? It's a quadratic. It doesn't have a third derivative, right? Now, is this going to be 100% accurate? Is it a perfect equation? Is it an approximation? It's perfect. It's a quadratic, right? I've got the second term. There is no error left, okay? How am I going to minimize this guy? How would I minimize this guy? So how would I minimize this guy? Can anyone tell me? Yes. Just hand her the sheet, please. How would I minimize a function in general?
If f of x naught is 0, then
What is the standard technique you used in high school to minimize a function? Find the derivative and equate to 0. Okay, what is the derivative of this guy? With respect to x, correct? Yeah. What is the derivative? It's going to be f prime of x0, because that's the only thing left over here, correct? Plus, what does the second term give me? Somebody, what is the second term giving me? It's going to give me f double prime of x0 times minus x minus times x minus x0. Equate this to 0. So what is the solution I'm going to get? What is the solution I'm going to get for x? X is going to be x0 minus f double prime of x0 inverse times f prime of x0. Correct? Is this making sense to everybody? Raise your hands if it is. Okay, guys, I need you guys to be more active. I shouldn't be the smartest person in class because I'm not. I need to be the dumbest person in class. You give me the answers, okay? Right. Now, can you relate this equation over here to your gradient descent update rule over here and tell me what the optimal step size must be? Viraj. What is the optimal step size?
something proportional to the second term, which is the ratio of the first to the second derivative.
What is this guy? That's just dy over dx, right?
Yeah.
So what is this guy? That is the step size, right? So if my step size is, if my eta equals f double prime of x0 inverse, I'm going to go from here to here in one step. Correct? And what is f double prime of x0 over here? That's just a. So if the step size is a inverse, I'm going to get there in one step. Okay. Now let's move on. If my step size is less than the optimal step size, what will happen? I'm going to go like this. Okay, what happens if my step size is greater than the optimal step size? I'm going to go here and then back here, right? Is there a step size that's so large that I'm not going to get to the minimum? What is that? So if my step size is greater than something that goes here, I'm going to take off. And what is that step size? 2 times, right? 2 times the inverse of the second derivative. And so you can see how the same equation can give you different solutions based on the step size. Everybody clear, right? Raise your hands if you got all of this. Okay, so that's basically what I'm saying here. The slide, it says that the optimal step size is the inverse of the first A over here. And if your step size is lesser than the optimal step size, you're going to go slowly to the optimum. Ideally, you want it to be as close as possible to the optimal step size. If it's greater than the optimal step size, you're going to oscillate. If it's too large, if it's more than twice the optimal step size, you're going to diverge. Right, yes, Neil?
Where does the 2 come from?
Okay, here. This is a symmetric function, right? This distance is the same as this distance, which is on the other side. Correct? So once the step size is going to go here, twice the step size is going to go here. Yeah, Viraj?
So this works for the second degree equation till now. But what if we have something that is a higher degree?
You'll get there. Okay. Bear with me, right? So everybody clear about this so far? This is for your second, one more slide, Viraj. If I have something that's higher degree, then at each point I can approximate it with a second degree equation, right? And if I use a second degree equation, this guy here is going to give me the optimal step size for that second degree Taylor series approximation. That's your so-called Newton's update rule. That's what you always do, right? And if your step size is more than twice that much, you have no guarantees that you're actually going to get to the minimum. Everyone clear? Right. Okay. So that's okay. Now, this was for a function of one variable, okay? Let's look at a function of two variables. I won't actually get into, I have a lot of math on the slides, but I think it's easier to think of it in terms of pictures. Pictures are nicer. So if I have a function of two variables, then the function, as we saw, let's assume that the function is aligned to the axis, because rotating the axis basically gives you off-diagonal terms on the Hessian. That's all it does, right? So it's convenient to think of the function is aligned to the axis. If the function is aligned to the axis, then that means that basically I have some function of this kind, x and y, x1 and x2, and this is a function of both, right? I'm going to assume that it's a quadratic in both. Okay, so along this axis, it's a quadratic. Along this axis, it's a quadratic as well, okay? So if I look at this function from the top, it's a bowl. The overall function is a bowl, and the function is going to look something like this. If I make slices at equal heights, each ellipse shows the locus of the x1, x2 values when the function takes a specific value, right? And what more? So I can write this as quadratic in x1, qx1 plus qx2, right? At different values of x2, this term changes. Q stands for quadratic, is the entire quadratic function, right? So if I look at different values of x1 and look at it as a function of x2, all that changes is that this first term changes, the second term stays the same. The first term is simply adding a height to the function, right? So all of these curves are going to look like these different quadratics. Will all of them have a minimum at the same point? Yes or no? How many think yes? Yes. Right? So similarly, if I slice along the other direction, every slice is going to be a quadratic, right? And they're all going to be quadratics at different heights, and they all have the minimum at the same point, and both sets will have a minimum right here in the middle, okay? Now, I can write this as a sum of two quadratics. This is the, it's one quadratic plus everything related to the second guy, or you can think of it as the second quadratic, plus everything related to the first guy. So here are the quadratics with respect to the first variable. It's going to be some a11 w1 squared plus blah, okay? Here is the quadratic with respect to the second variable. It's going to be a22 w2 squared plus some blah, right? If I were to use a minimum optimal step size for the first quadratic, what's it going to be? I have the answer on the slide. Okay, it's going to be the inverse of a11. If I use the optimal step size for the second quadratic, it's going to be the inverse of a22, right? And so, yeah.
What is the 1 minus 2?
So basically, I'm speaking of, this is x1. I'm calling it w1 and w2. It's a quadratic along this axis and this axis. So I'm calling the quadratic coefficient here a11, and the quadratic coefficient on the other axis a22, right? Make sense? Okay, so where does all that take us, okay? Now, if I'm using gradient descent, here's what happens. When I'm using gradient descent, this is the gradient update rule that we use, right? You take a step against the gradient, which means the step size is the same in every single direction, right? Does anybody see a problem with this? To see why that's a problem, let's skip all the math again. Here is one example, right? This guy, now go back here. The optimal step sizes can be very different in the different directions. Correct? Everybody sees what happens over here. So if I get an equation figure of this kind, so here the optimal step size in one direction is 1, the optimal step size in the other direction is 0.33. Can anybody tell me which is the direction where the step size is 1 and which one is 0.33? When the optimal step size is 0.33, it means that the function is steeper, right? You want to take a smaller step, right? So the horizontal is probably going to be 0.33, the vertical is 1, right? Okay. Now, suppose I take a step of step size of 2.1 times the optimal step size for the second direction, right? That's going to be, say, like 0.7. If I have a step size of 0.7, step size of 0.7 is less than 1. Okay. So in the vertical direction, it's sort of converging slowly towards the optimum. But it's greater than twice of 0.33. In the horizontal direction, it's going to diverge. Okay. Here, I have a step size of exactly twice of 0.33. This is still less than 1, right? In the vertical direction, it's going to come down slowly towards the optimum. In the horizontal direction, it's just going to keep bouncing around, right? Here, it's 1.5 times 0.33, right? So it's less than 0.66, which means it will come to the optimum in the horizontal direction, but by going back and forth, right? In the vertical direction, it's going to come slowly down to the optimum, right? And so you're going to get this behavior. And over here, now this is the nice one, right? The step size is 0.66, which is exactly the optimal step size in the horizontal direction, but much smaller than the optimal step size in the vertical direction. So in the horizontal direction, it gets to the right point in one step, then takes its time coming down, right? And if it's lesser than this in both directions, it's going to come down very slowly. Yes, Yingxin?
Does it make sense to have different step sizes?
We'll get there. Okay, right. So yes. The question is, how do you compute it, which becomes a much bigger problem, all right? So what does this really mean? You want the step size to be as close to the optimal step size as possible, or you're going to take a very long time to get to your answer, right? But then, if your step size becomes too large, you're going to blow up. And when you have many different directions, in a neural network, you'll have 1 billion different directions, right? So the optimal step size must be smaller or equal to the optimal step size, twice the optimal step size for the fastest direction, correct? Otherwise, when you're trying to get to the correct answer in the other directions, this one is going to explode, right? And so what we will find is that the optimal step size has got to be less than 2 times the smallest of the optimal step sizes in the various directions, right? But that means that it's going to be very slow in the other directions. It's going to take forever to converge. Everybody get this? Right. And so this is for quadratics. I can do this even if the function is not a quadratic using the same trick that we did before. If I have a non-quadratic function, I can use a second order Taylor series expansion. And the optimal step size is going to be dependent on the eigenvalues of the Hessian, right? And if you have the largest, the optimal step size has to be less than twice the smallest eigenvalue for the Hessian, right? So Chenda, can you flip the phone over? Yeah, right. And so here is what we find, that if this ratio in the different directions is the ratio of the largest optimal step size to the smallest optimal step size, what we will call the condition number over here. If that is large, you're going to have real troubles optimizing your function You want that to be as small as possible, right? And a lot of the things that people do in optimization, normalizing by Hessian, normalizing the objective function, scaling the variables, etc., all of it has to do with trying to get this one as close to 1 as possible so that you can get to the answer very quickly, right? Oh, is all of this making sense to everyone? Raise your hands if it has. Okay. Now, so the question is, again, do I really have to be this careful? Or am I missing something obvious? Okay. I'm missing something obvious, obviously. What is that? My loss function doesn't look like a bowl, it usually looks like this. You have no idea where you're starting, right? I could end up starting over here. If I use the optimal step size for that, for the current location, or something close to the optimal step size that prevents divergence at the current location, I'm just going to end up over here, right? So what do you really want? You want you want to escape local minima, but you don't want to escape global minima, right? What would your strategy be in this case? Anyone want to tell me? Yes.
Maybe start with a bigger step size.
Thank you. Yes. That's exactly what we will do, right? We will start with a larger learning rate, greater than twice the optimal step size for the current position. And that means that you're going to initially diverge. But then the assumption is that when you actually come to global minima or decent minima, the decent minima have large bowls. So you're going to start with a large learning rate and then keep decreasing the learning rate. And if you do this gradually enough, eventually you're going to end up in a large bowl, which is probably, and a small step size, which is probably going to be the global or a decent minimum. So you don't want to always be convergent. You want to start off divergent so that you can escape absurd situations like these, and then finally converge to either here or here, depending on your luck, right? So this means that, yes?
So, Professor, doesn't that rule of thumb may not be applicable all the time, right? It depends on where you start, right? Because let's say you want to be divergent, but you are actually like close to the global minimum.
If you keep decreasing it, imagine a quadratic. You would go up and then come back down because you're decreasing the step size anyways. So it's going to apply, right? You will diverge, but then eventually come back because the step size is decreasing. And so which is why you have all of these typical delayed learning schedules that you see in your homeworks. You don't have a constant learning schedule. You start off with something large and shrink it. And there are different ways of shrinking it. There are different functions that you will see. We will see a little more on how, what are the criteria for these learning schedules in a couple of classes from now. But starting with a large learning rate and decreasing it with the iterations makes a lot of sense, right? We see why. We will see how in a couple of classes. So gradient descent can miss obvious answers, but this may be a good thing, right? And yes?
Yeah, well, like if we do not reduce gradually reduce the learning rate, it should still do the same thing if like the bigger boat has like, the threshold is larger. So like, for example, like the bigger boat has the threshold.
Yeah, depending. On some loss functions it would work, for most of them it wouldn't. Right? You're going, because whatever your step size is, you'll end up in a bowl for which that step size is optimal if you retain the large step size, which might not be the one you're looking for, right? Yes. This is where all the heuristics that you end up with when you're training your network. We really don't know. We cannot characterize these loss functions because they're loss surfaces because they're hideous, and they live in billion-dimensional spaces, right? Or hundreds of millions or tens of millions, anyways. So a lot of it is empirical. There's one more poll. I'm hoping you can find this poll. get it?
Yeah.
5 seconds, guys, because I'm running out of time. All right. Let's move on, right? So step sizes that are greater than twice the inverse of the second derivative can cause gradient descent to diverge. This may not be a bad thing, right? Gradient descent will not converge without decaying learning rates. Again, as Chenda just pointed out, it can converge. It just might not be the one that you wanted to converge at, right? So divergence causing learning rates may not be a bad thing, particularly for ugly loss functions. Decaying learning rates provide good compromise between escaping poor local minima and convergence. Many of the convergence issues arise because we force the same learning rate on all of the parameters, which is what somebody else pointed out. So let's try to change this last criterion. Let's try to say we can use a different learning rate on each parameter, right? And let's say instead of having this constant step size for every parameter, we're going to have a step size that's specific to the parameter. The problem is, how do you find the step size? You're going to be keeping track of 1 billion different step sizes, or however many parameters you have, and finding the optimal one for all of them is going to be a challenge by itself. So we need some heuristics for working these things out, right? So there were several derivative inspired algorithms that sort of try to do the right thing in each direction independently. And here's the problem, right? If I just find the optimal step size independently for each direction, there is no guarantee that I will actually find the overall optimum solution, right? And here's the thing. When I'm doing gradient descent sort of tells me I'm going in the direction of decreasing loss function, but only if I'm going against the gradient, which uses a constant step size for all of the directions, right? If I use different directions and different step sizes in different directions, while I might want to go this way, I may end up going in a completely different direction that actually ends up increasing the loss. So simply saying I'm going to take independent step sizes in every direction may not work at all, right? So you've got to figure ways around this, and a lot of what we do actually tries to sort this out. Now, one of the earliest techniques was RProp, resilient propagation, which allows each direction to be independently updated, but uses some simple heuristics. Again, let's skip the text on the slide and let's see this with figures. Here's what we'll do. We are going to do this independently for every direction, meaning this rule, I can plot RProp using just one curve, because the same heuristic is going to be applied for every single parameter, every single direction, right? Each parameter has an initial value. So I'm going to have some function value at the initial estimate, and then I can check the derivative at that initial value, right? If the derivative is negative, I have to go forward. If the derivative is positive, I have to go backwards. Let's assume, without loss of generality, that the derivative is negative, right? So the first thing you will do is, okay, you have an initial step size, and then you take a step over there, right? If you take a step over there and the derivative, the sign of the derivative has not changed, it means you're going in the right direction, right? Things are continuing to decrease. Given this, would you want to increase your step size or decrease your step size? If you're doing the right thing, you want to do more of the right thing, right? You're going to take a larger step size. And then when you take a larger step size, you might find that over here, you end up at some other spot, and then you find that the derivative still has the same sign. You want to increase the step size again, right? So every time the sign of the derivative is the same as the sign of the derivative after the step is the same as the sign of the derivative before the step, you're going to multiply your step size by some term alpha, which is greater than 1, because you're taking a larger step size, right? But now suppose this larger step size takes you across the minimum. Then what will happen? What happens to the sign of the derivative? It's going to flip, right? If it flips, if I were to ask one of you what would be the reasonable thing to do, what would it be? you can go right back, yeah, and now take a smaller step, right? So what this means is that you take an initial step. If that step takes you to a place where the sign of the derivative is changed, then you go back and now multiply that step size by a term beta, and what must beta be? Smaller than 1, and then repeat the process, right? It's a very simple algorithm, nothing fancy, right? Very, very simple. And you're going to do this for every single dimension independently, and it's going to get you to the minimum. So this thing is the resilient prop, R prop. It's a very nice and very trivial algorithm, and the code for it is not particularly complicated. Where does backpropagation actually turn up in this entire process? Where does backpropagation turn up? Anybody want to tell me, Ijia? Where does backpropagation turn up? You should turn your phone off. Okay, so where does it turn up in this process? Pardon me? Calculating the derivative. If I want to calculate the sign of the derivative, I need the derivative. You still need backpropagation, right? Backpropagation will give you the derivatives, it will give you the sign of the derivatives, and you can use this rule to actually update your parameters. Very simple. And again, I have pseudocode for it, but the key point is the logic is very simple. I'm going to take a step, and if after taking a step I find I'm going in the right direction, I'm going to take a larger step. And I'm going to keep doing this until I find that I've overshot. And it's very easy to check if you've overshot. If the sign of the derivative has flipped, that means you've overshot, right? And then you take a step back and repeat the process. Where can this break? Can anyone tell me? What kind of situation can it break in? Yeah?
So maybe the minimum at one dimension is the max in another dimension?
No, even now, that's getting too complex, right? Yeah.
If you take more than 2 times.
So if I have something like this, right? And I may actually go from here all the way here. And the signs are still going to stay the consistent, and I'm going to do more of the same thing. It's going to get worse, right? But then, oddly enough, this works really nicely. It's the simplest algorithm you can think of. It still works excellently. If you could implement it, I find it very peculiar that you don't actually find it being used a whole lot more, but it's very easy to implement, and it's highly effective. Yeah.
Is R prop basically mean by training in one dimension only each time?
No, in each iteration, you're going to be using this rule independently for every dimension.
Oh.
Correct?
I see.
So you're not optimizing one dimension at each time. In each iteration, you'd be doing this for every dimension separately, right? Going too fast. Okay, 5 seconds, guys. I'm running out of time. Yes?
I have a question about last slide. What's the minimum condition you said? Only make minimum assumption. What's the assumption?
You're not assuming that the function is convex, right? So but you are assuming something of this kind. You're assuming that the function has maybe of this kind. That's not convex. But the signs of the derivatives stay consistent on either side of the minimum. That's the only assumption you're making.
You mean like the function doesn't have a very deep value?
It could be. That's not the point. The point is that as you approach the minimum, the sign of the derivative doesn't change. That's all you're assuming. This is not a convex function, right? If I just connect these two guys, it's going below the function. So you're not making convexity assumptions. It's more general than that. Okay. We know the answer to this, right? Now there's another variant of the same. There's another variant of the same philosophy called quick prop, which is even more effective than rprop. This was invented by our own Scott Fahlman many years ago, and for many years it was ignored. Then people discovered it, and it became very popular. But then lately it's sort of become less popular again. So quick prop. The thing with the optimal step size is that the optimal step size requires you to compute the second derivative. Computing the second derivative in a function that's as crazy as a neural network is very hard. So quick prop uses an approximation. It says it computes the second derivative as the difference between two steps and uses that to normalize the step size, and gives you one of the fastest converging training algorithms that are still around, right? Anyway, so here's what we found. Second order methods that can normalize the variation across dimensions. If I have something of this kind, if I have what did I do with my chalk? If I have a bowl of this kind, the obvious thing for me to do is to scale my space, right? Shrink it along the vertical axis, stretch it along the horizontal axis so that it begins to look like a circle, at which point the optimal step size in every direction is the same. But that requires multiplication by the inverse of the Hessian, which was again, the inverse of the second derivative. That's what it's doing. And it's too complex. Nobody ever does it. You want adaptive or decaying learning rates to improve convergence, but more importantly, methods that decouple the dimensions can improve convergence, except they come with their own challenges, right? But in spite of all of this, you still have an issue, which is that, in fact, they have several issues. One of them is that if you have something like a saddle point, you want your algorithm to keep pushing forward, just to make sure that you escape the saddle point and maybe you go towards a genuine minimum, right? Whereas if a function only tests the derivative, it's going to stop there and then you're done and you're not going to go any further, number one. Number two, you have situations such as these where, you can have the algorithm sort of slowly converging in one direction but diverging in the other direction, right? Suppose you start off with some step sizes and you find that the algorithm is doing this. What would you want to do to the step sizes over here? So suppose you're allowed to decouple the step sizes, what would you do? Would you lower the step size in every direction? Then lower the step size in the horizontal direction and increase the step size in the vertical direction. How do you find out, which way to go, right? Which direction requires the lower step size and which direction requires the larger step size? So here's what momentum-based method, what we want to do is we want to keep track of these oscillations. You want to emphasize the steps in directions that converge smoothly. You want to shrink them in directions that oscillate or diverge, right? And so this gives us the so-called momentum methods. I will just introduce the general idea. We won't go over it in this class. We will go over momentum methods in more detail when we're talking about stochastic gradient descent, okay? But what we want to do is to maintain a running average of all past steps, okay? Now, if I'm maintaining a running average of all past steps in this scenario, what is the running average of all past steps in the vertical direction? Is it going to be large or small? It's always positive, right? So the average is going to remain some positive number. What about in the horizontal direction? It goes positive then negative, positive then negative. When you take an average, what will happen? It will cancel out, right? And so you want a strategy that looks at how these things, this is following up on the rprop philosophy, correct? You want a strategy that looks at how the derivative has been behaving in each direction in the past few iterations. And in order to figure out what best to do, you're going to sort of emphasize steps where the derivative has been behaving nice and consistently. You're going to de-emphasize steps in the directions where the derivative has been bouncing around, which means that, and the simplest way to figure out how to do this is to just to compute an average. If this is, if things have been bouncing around, you expect the average to be small. If things have been consistent, you expect the average to be large, right? And so that gives us these so-called momentum method. I'll stop right here, where the idea is very simple. You're always thinking of the current step size, and the current step size is going to be the current gradient plus some fraction of the previous step. That is the definition of a running average, right? A running average is you've got a running average. Then when you get a new step, you just start off averaging the new step with the old step. That's the running average, right? So this is literally just the running average. And observe that this equation is no longer being written in terms of individual components. I'm just thinking of this as a general step size, right? And this one generic equation, which is still written in vector form, manages to do the right thing by cancelling out oscillating directions and enhancing the consistent directions, right? So this is the so-called momentum update. We will revisit this in a couple of classes from now. Any questions? Yes?
Just like you mentioned, like before, if we use different update learning rate in different directions, we will end up like on wrong direction.
So in this particular case, right, for some classes of functions, it's provable that this gives you the optimal. It doesn't effectively decouple, right? It's sort of there's no explicit decoupling over here. So you're following trends. Yeah. No, it's going to, you're following global trends. So you're just maintaining a running average of the gradients, and you can show that it will converge faster. Yeah. I can't hear you. Everybody's, yeah. So the axes, they're going to be orthogonal in some direction, right? So we're assuming that the directions are different. That's all it is, right? We're not making any assumptions about the axes. There is no assumption about the axes over here. Unless I missed your question. Maxwell, what was your question? I can't hear you guys. Let's take this offline, okay? All right, guys. If you have any questions, post on Piazza, right?